Good day and welcome to our class. Today we shall be talking about contour integral in complex analysis. If f of z, if a complex function f of z is defined single valued and continuous, we define complex integral as this. We define complex integral as this. Let's recall that f of z is u plus iv, while dz is dx plus I dy, because z is x plus iy. Now let's substitute what we have there. Let's say I is the integration. F of z will now become u plus iv, the z will be the x plus I dy. If you expand, you have u dx plus I u dy, and this one plus I v dx, and this one will be minus v dy. That is the expansion. And if you rearrange it, real part to real part, imaginary part to imaginary part, you have u dx minus v dy, then plus I into u let's say v dx plus u dy. So this is expansion of complex integral, and it is used in what we call contour integral. I've shown here that complex integral here can also be expressed in terms of real part and imaginary part, which will help us when we are dealing with complex integral. Let's now consider Riemann definition of complex integration. The Riemann definition of complex integral is given as this: integral f of z is z equal to summation r runs from 1 to n f of si r zr minus zr minus 1. We call it this a Riemann integral for complex integration. In this case, we assume that f of z is continuous, but it may not be analytic. That's our assumption. And this e here, si here, si1 to sin, they are points that lie on this zr minus z is. Now let's consider this theorem. So we call it ML inequality. That theorem, we call it ML inequality. This is the theorem: if a function is continuous and integrable on a contour C of length L, and if this inequality is satisfied, that is, if f of z is bounded, this inequality is satisfied, then absolute value of integral f of z is z is less than or equal to ml. This is called ML inequality. Now let's prove the theorem. By elementary calculus in real analysis. By elementary calculus, we know that this length of arc is given as this: the s over the t all squared plus the y over the t all squared dt. We know that. Now the z will be equal to the x plus I dy, which we have known. Let's put absolute value to both sides. Therefore, absolute value of z will be equal to absolute value of dx plus I dy. And we know absolute value simply means square root of real square plus imaginary square. That is this, the s all squared plus the y all squared. Now let's integrate both sides. Integral of the z will be equal to integral of square root of the x plus the y all squared, which I can still write as square root of the x all squared plus the y all squared. This everything over the t here times the t. So that if I cancel the t, it will still be the same thing. Now this dt by indices, by surd, I can bring it in, it will become square. This dt will become square if I take it into square root. Therefore, our integral, our absolute value of integral, our integral absolute value of the z would now be equal to square root of the s over the t all squared plus the y over the t all squared, which, and this one we have seen that it is L. Therefore, our integral of absolute value of the z is equal to L. Also, we have seen that f of z2, absolute value of z, is less than or equal to m from this place, from the theorem. Now, from Riemann definition of a complex integral, we know that integral f of z dz, we know that is equal to summation r goes from 1 to n f of si r into z arc minus z arc minus 1. So if you put absolute value to both sides, put absolute value to both sides, put absolute value here, if you put absolute value here, you have put the absolute value. This will be less than or equal to. Why? Because from triangular inequality, which says a plus b plus c and so on, the absolute value will be less than or equal to absolute value of a plus absolute value of b plus infinity, like that. Therefore, absolute value of f of z dz will be less than or equal to putting the absolute value inside. R goes from 1 to n, absolute value of f of si r into absolute value of z minus this. But we should take note that this one is dz. And f of z is less than or equal to m already, so this is m, while the z is equal to L. This is L. So we can now conclude that absolute value of z dz, integration, the integration, let me write it better. Is less than or equal to m. So this we consider contour integral now. That is a complex line integral. When we are evaluating a line integral in a complex plane, we call it a contour integral. And the only thing we need here, we are familiar with line integral in our linear analysis. So the only thing we need here is that integral f of z dz is same thing as u ds minus v dy plus I into integral v dx plus u dy, to be very effective. Now let's take example. Example 1. The question here: evaluate the line integral this, which moves along curve C, which moves along the path this and this, along the line joining this point and this point, and along the line joining this point and to this point. Now we are given 2z plus 3. The first thing is we need to know what is our x and what is our u and what is our v. Z is s plus iy plus 3. If you expand and rearrange, we have 2s plus 3 plus iy. So without stressing ourselves there, plus 2y, because 2 times y is 2y. You will now see that our u is 2x plus 3 and our v is 2y. The first one says integral f of z is z. This is what we are going to be using. U dx. This is our u. 2x plus 3 dx minus v dy. This is our v. 2y dy plus I into v dx. 2y dx plus u dy. This is our u. This is our u here. 2x plus 3 dy. But in A, okay, this is what we'll be using now. In A says s is this and y is this. Let's substitute it there. S is 2t plus 1. If you differentiate, the s will be 2 dt. Y is 4t squared minus t minus 2. Then the y is, if I differentiate, it will be 8t minus 1. Then dt. Then the integration becomes, the boundary we are going to use has been given to us 0 to 1 for the value of t. 0 to 1, 2s plus 3. Our s is here. Our 2s plus 3, that is 2 times this plus 3. That will be 4t plus 2 times 1 is 2 plus 3, 5. Then dx. Our dx is 2 dt. 2 dt minus 2y. Our y is this minus 2y. 2 times this, that is 2 times 4, that is 8t squared minus 2t minus 4. Then dy. This is our dy here. This is our dy. Dy is 8t minus 1 dt plus I into 2y dx. This is our y. Our 2y will be 8t squared minus 2t minus 4. That is 2y dx. This is our dx here. Our dx is 2 dt. 2 dt plus the last one, 2s plus 3 dy. So these are 2s plus 3 here. That is 4t plus 5 dy. Our dy is, let's say, times 8t minus 1 dt. 0 to 1. We are now left with the integration of this. We need to integrate this with the boundary. I don't need to do that. You need to expand this, integrate with the normal integration. When we do that, we should get 17 plus 19i is our answer. For the second one, which is B, B says along the line joining this and this. It's been given already. We don't need to stress ourselves here, because since it is z directly, we can just integrate directly. We don't need to use the formula. What is now given to us in B is 1 minus 2i to 3 plus I 2z plus 3 dz. We just integrate directly. That is, if you integrate, that will give me z squared plus 3z. 1 minus 2i 3 plus I directly. This will now give me 3 plus I squared plus 3 into 3 plus I. As usual, minus, we put it here, 1 minus 2i squared plus 3 into 1 minus 2I. Then we need to simplify this, which I have taught before. When we simplify further, we are going to get 17 plus 19I. Just as this one. We get 17 plus 19I. Now, the third one says from 1 minus 2I to 1 plus I, and then to 3 plus I. For this one, now this one is having more, so I will need to use this fact here. I will need to use this fact, the one we got here, to be easy for us. When we use that, 2x plus 3 dx minus 2y dy plus I into 2y dx plus 2x plus 3 dy. I will not do like this. I will say from 1 minus 2I to 1 plus I. From 1 minus 2I to 1 plus I. This is what we are going to do. This one, we write it as 1 comma minus 2. This one will be written as 1 comma 1. So we apply equation of a line which says y minus y1 over s minus s1 equal to y2 minus y1 over s2 minus s1. As we normally do inside the real analysis. If you apply it here, you will see that you get s is equal to 1. If you get s is equal to 1, then ds will be equal to 0 if you differentiate. Now let's substitute whatever we get here. S is equal to 1. Then I1, which is integration, will become 2x. S is 1. So it will nullify. In fact, there's ds here. It will nullify the whole thing. ds is 0. It remains minus 2y dy there plus I into here 2 is 0. What we have left is 2x and our s is 1. So 2 times 1 is 2 plus 3. This is 5 dy. Now, what boundary are we using? It remains only y. So we are going to use boundary of y, which is minus 2 to 1. Minus 2 to 1. Minus 2 to 1. You can as well apply it here. You get the same thing. And when we integrate, when we simplify and integrate, we are going to get 3 plus 15i. Now, for the last one, we can now say that from or along this path, 1 plus I to 3 plus I. So this one gives what? Let's say this one is this to point C, 3, 1. If you apply this formula, you are going to have y is equal to 1, so that the y will be equal to 0. So when we see apply it here, our I2 will become 2s plus 3 dx. 2s plus 3 dx. It will nullify this because the y is 0. Plus I into 2y. Our y is 1. So that will just be 2 ds. The whole of this is 0 because the y is 0. Now, we have only dx left. So we are going to make use of x values. These are x values. 1 to 3. Integral 1 to 3. When we now integrate, when we integrate this, which I will not show, when we integrate it, we have 14 plus 4i. Therefore, the integration f of z dz will be I1 plus I2. And our I1 is 3 plus 15i plus I2 is 14 plus 4i. Adding it together, we have 17 plus 90i. So, you observe that all of them yield the same result. So that means this function is independent of the part is moving. This given function is independent of the part that is moving. Second question, evaluate this line integral where C satisfy all this. The first one is circle of 2. Now before anything, let us first express this in terms of u and v. 1 plus z square. We know that z is 1 plus z, s plus iy, then all square. If we expand and simplify, we are going to have this and this. Therefore, this one will be our u, while the other one will be our v. Now, the integral becomes, if you apply u ds minus v dy plus I integral v ds plus u dy. Now, for this circle, the circle here, absolute value of z is equal to 2. We are going to have this. We know that absolute value of z simply means square root of s squared plus y squared. And if we transfer the square root to the other side, it makes this 2 to be 2 squared. Making y squared the zero formula, we have this. We can still make y the zero formula, that is square root of 4 minus s squared. But we are coming there. Therefore, the integral f of z dz will now be equal to s squared minus y squared. S squared minus, these are y squared. That is minus 4 plus s squared plus 1 ds minus 2x. This is our y. 4 minus s squared. That's our y. Then dy. So dy there means I should differentiate this. And if I differentiate this, I will have x over square root of 4 minus s squared. There will be plus here because there is minus here, then dx. So that this cancels this at the end of the day. Then plus I into 2xy. This is our y. Dx plus s squared minus y squared. This is our y squared here. This is our y squared. 4 plus s squared plus 1. Then dy. This is our dy here. X over square root of 4 minus s squared ds. Now because of that minus, it will nullify this plus. It will make it to be minus. Now we have everything as x values. So we are going to apply x for it. So in that case, we are going to have the x value will be 2 to 0. 2 to 0, 2 to 0. The boundary of the integration. Now, we can simplify this further. This cancels it. This is 2s squared. This is 2s squared. When we simplify it further, we should be able to have, it should be, this is s squared, and 2s squared. This cancels this. We have 2s squared. That is 4s squared. Because we can turn this upside down, it will become minus 4s squared. And the other constant there, this is 1. This is minus 4 plus 1. That will be minus 3. It will become 3 because I want to turn this 0 to 2 instead of 2 to 0. Then dx plus I into, I'll turn this one to 0. When we simplify, we still have 4s squared minus 11x over square root of 4 minus s squared dx. So this is all we have. So we are left with integration of this. So how do we integrate this? This is normal integration. We let s to be 2 sine theta. Then ds is 2 cos theta d theta. We substitute there and simplify. When we do that, we should be able to have minus 14 over 3 minus 2i over 3. So you need to show me how you get this. Check the solution. Now for the second one, along BO, z is equal to 2i and z is equal to 0. For B, along BO, z is equal to 2i, z is equal to 0. So you can see that that one is 0, 2. This one should be 0, 0. So when we apply equation of a line that I put here, this one, when we apply it, we should be able to get s is 0, then the s will be equal to 0. So in this case, anywhere you see s in this place, we'll put it as 0, and the s2 is 0. In fact, it nullifies the whole of this. This one too is nullified. It will remain only this. It will remain only integral f of z dz to be equal to plus I into minus y squared plus 1 dy. So this is what we are going to have left. This is it. Once again, this is minus y squared plus 1. That's what we are going to have left. And that is what I wrote here. Now we have only y. Only y there will now become, because we are dealing with only y, it will be 2 to 0, which we can write as I into 0 to 2. It will now be y squared minus 1. This is I into 0 to 2, y squared minus 1 dy. So it is now very easy for us to simplify here. This will give me 2i over 3. And the last one there, along OA, our O is z is equal to 0, which is 0, 0. And A, that is z is equal to 2, is being given here 0 and 2. So that means this one will be written as 2, 0. So when we apply equation of the line here, when we apply it, we will see that you get y is 0, then the y is also equal to 0. Now if you substitute that inside this place, y is 0, it remains s squared plus 1 dx. This one will be gone. This one will be gone. The whole of this will be gone. What we are going to have left is s squared plus 1. In that case, integral f of z dz will be equal to s squared plus 1 dx. Since we are dealing with dx now, we are taking the values of x, that is 0 to 2. So we will now integrate this. So when we integrate it and simplify, we should be able to get 14 over 3. So that's our answer. So if you now decide to add all these results together, the results in A, B, and C, this is our A, this is our B, this is our C. We can say that f of z dz would now be equal to minus 14 over 3 minus 2i over 3 plus 2i over 3 plus 40 over 3. This will be equal to 0. So the integral f of z dz is equal to 0. F of z is 0. And since it's 0 like that, this satisfies what we call Cauchy's theorem, or what we call Cauchy integral theorem. So the f of z dz is 0. And we observe that this function is analytic everywhere. So if a function is analytic, Cauchy's theorem says that the integral of that function will be equal to 0.